Welcome, everybody, to the first ever nTop Computational Design Summit. It's such an amazing moment for me to see everybody here from the different phases of nTop, from early adopters to people that have started to pick up nTop a couple years ago, to new users of nTop, to all of our partners. And so it's really a special moment for me to see everybody in the same room together for a day where we can really talk about computational design. And so I thought, what better way to start off the event than to make a movie to kind of show off some of the power and the precision of nTop 5 by remaking the Powers of 10, which was a film made in 1968 to kind of give us a sense of the scale of the universe. The idea here was to really give a sense of the scale of the universe of nTop 5. And so today is a really important and special day to talk about the universe occupied by our customers, our partners, and the products that our customers make. And so I want to talk a little bit about computational design. But first, I really want to talk about, what are the problems in the industry, right? Our customers span industry from aerospace, medical, to automotive, industrial, and consumer. And across all of these segments, the one thing that we see that's kind of a standard is that there's more pressure than ever to deliver high-performance products, whether that's in aerospace to make more sustainable, faster aircraft, whether that's in medical device to make more integrated, osseointegrative medical implants that merge with bone, or automotive to make less expensive, more cost-effective vehicles that don't require carbon energy, to the industrial segment, to decarbonizing our world, and to the consumer segment, to making more sustainable products for the world as well. And so if you look at the delivery of high-performance products, what's the constraint today? And so it's our belief that the traditional tools today are constraining high-performance part design. And that's really for three reasons. Well, first off, traditional engineering tools normally require manual modeling of low-level design features. This is a screen recording of a group at Lockheed Aerospace modeling the bulk panel of a bulkhead for something like an F-35 aircraft. All of those ribs and stiffeners are manually defined, manually edited. And so every time there's a design change, that model needs to be updated. Second, it's really difficult to set up the complex set of relationships needed to solve hard engineering problems. And so here's an example of a manifold for a rocket component. And what I would want to do here is parameterize the sizing of that manifold to match some inlet pressure on the tube coming in and some outlet pressure on the ring going out. Just setting up that relationship is a very difficult issue. And then once you do have that relationship set up, changing the size and scale of that part is really, really challenging as well. Lastly, the physics. All of these components exist in the real world, right? Like our customers, you guys are not making video games. You're making parts that need to go at supersonic speeds, or exist underwater, or exist in a human body. There's a complex set of physics interacting with these components, and those physics are sometimes difficult to capture. And then once they can be captured, what's even more difficult is using those physics to drive important design decisions. And so this technical problem actually creates a problem which is the iteration through a design, right? These high-performance designs require a lot of iterations to get right. Design iteration today is not fast enough because using traditional tools, you basically have the same amount of time. Every time you design a part, learn something, make a change, redesign it, all of those tools become a bottleneck. And so as an industry, we've kind of been stuck to this speed of iteration of the speed of manual iteration. And so let's talk about computational design for a second. So the way that we define computational design is the process of capturing design intent in a language that computers can understand, first off. And the idea is that the computer can help to generate solutions to these complex engineering problems. And so use the term algorithm, right? The design logic for computers to understand and help iterate through these design problems, that logic has to be captured into an algorithm. So what does that mean? Something simple like an airfoil, right? This is kind of how we as engineers would understand an airfoil shape, parameterized by some thickness and camber fields. That model needs to be captured. That logic of creating that airfoil needs to be captured in a set of language that computers can understand and then process. In nTop, we have the block system. This could be computer code, et cetera. And secondly, once that logic is captured in a set of language that computers can understand, computers could be used to generate, to visualize, explore the vast design spaces that make up these computational design problems and these high-performance parts, right? Because when you're capturing that computational model, that model doesn't just capture one version of a design as a traditional process would, but that computational model, by specifying those requirements algorithmically, that model actually calculates an entire design space or the entire art of what's possible in a model. And so thus, that speed to iterate is where we see computational design coming into effect. And so computational design is a new process, right? We need tools to, first off, build and construct a computational model. Second, we need tools to then run a computational model to explore that design space. And then third, once we've found an optimal design through exploring that design space, through learning, through iterating, that part needs to be integrated into the entire system. If it's the structure of an aircraft, that needs to be integrated into the digital assembly in CAD. There needs to be further validation downstream through simulation analysis. That part, again, I said it before, it needs to be manufactured, and so there's CAM. And so today we have a very exciting set of partners that we'll be talking about on the integration side, and I'll get there in a little bit. But the point here is that the building phase of a model might take a little bit longer than manually drawing that component, assuming you can manually draw it. But once that model is built, you can rapid fire iterate through that design, learning each iteration to get to a better design point. And so, computational design enables faster iteration, but ultimately, it's about designing better products and better parts. And so, I want to talk for a second about one of our customers, Seamen Energy. And so for those of you that know Seamen Energy, maybe you know the products that they make. For those that don't, Seamen Energy produces some of the largest gas turbine engines I've ever seen. So when I was on a flight here, or whenever I'm boarding a flight, I like to look at the engine next to me as I'm boarding in, and I see the size of the engine. It maybe is 6 feet. Their SGT 800 is 18 feet tall. These are gigantic. They're the size of school buses. These are some of the most complex products that exist on the planet. And so Seamen Energy has been deploying computational models to help them decarbonize these type of engines so they can run on hydrogen power, a sustainable energy. And so if we look at the types of models that they're building, Seamen Energy started by looking at models like filters and parts where the core modeling technology underlying nTop, the implicitly defined signed distance field, allows them to generate incredibly complex geometry incredibly fast. So this is a filter with 29,000 holes. In a traditional BREP-based CAD tool, it would be 200 megabytes of data. In nTop, it's 3 megabytes. The iteration time here is on the order of seconds to minutes versus hours or to days. Secondly, leveling up in building computational models, we also have computational models for deploying heat exchangers. So these are heat exchangers, again, to, when you're converting a large gas turbine engine to hydrogen power, getting the heat out is really critical to this engine. And so they're leveraging, again, the implicit modeling capabilities to more easily vary the different properties of that heat exchanger, like the wall thickness, the offset, et cetera. On to running the model. So running the model, once you've had that model built, Seamen Energy is exploring really rapid numbers of iterations through a model like this shell-thin heat exchanger for a traditionally manufactured cooling system. They were able to run 200 designs with only 23 errors. Using a traditional BREP-based CAD tool, they would be happy with about 30% of the results coming out successfully. This is close to 90%. And then the integration and validation. Integration and validation is absolutely critical here. And so once they've identified a final design, like the design of this ARPA supercritical CO2 heat exchanger to decarbonize, that heat exchanger needs to be integrated into simulation tools like STAR CCM for the analysis and validation, and then also it needs to be produced and manufactured and then tested as well. And so Seamen Energy is one company deploying computational modeling. Where nTop is at today, or as of today, we have a little over 400 companies again, across those industry, aerospace, medical, automotive, industrial, consumer, and manufacturing that are starting to integrate computational design into their design process and product development process. And so, at nTop, I didn't really talk about nTop yet, but what do we do at nTop? Well, nTop provides tools for computational design. And so if you look at that process, building, running, integrating, we have 3 products. nTop, which is the product that most of you are familiar with. This is our desktop-based product. What makes nTop unique is the core modeling technology, the implicitly defined sign distance field, which enables these models of, orders of magnitude more complexity than a BREP to be produced and designed and iterated on in real time, as we've seen in the powers of nTop. We also have a product, nTop Automate. You could think of these as like the nTop robots. So they can process and run massive amounts of nTop models in the cloud or locally to explore and produce the different variations on a design that you can learn from and then iterate on. And lastly, we have nTop Core, which is critical for our partners, right? Because we've produced these new models that are orders of magnitude more complex than traditional models that are defined implicitly as sign distance fields. nTop Core allows our partners to integrate those implicits directly, so you don't need to mesh. And so nTop models can be directly integrated. I'm going to talk a little bit about that. But for today, really, it's about what's next. And so I'm really, really proud of the team today. Maybe you've seen the press announcement go out this morning. We're launching nTop 5, which is available as of, I think, 2 p.m. today. Trevor, you can confirm that went out. Yes, awesome. So congratulations for nTop 5 going out today. And so we've been putting a ton of work in terms of improving our core modeling technology. We released a new core solid modeling engine. Internally, we call it Sequoia because it's modeled based on a tree, actually, and you can learn more about that from us. But with the new modeling technology, we've increased the performance and the precision by an order of magnitude in nTop. And we've seen that with the powers of nTop video. What I want to talk about now is really the interoperability improvements, because along with releasing our new core solid modeling technology, we're going live with a few really, really important integrations that I want to talk about. And so there's 3 levels of integrations of nTop into the environment. And some of our partners are here. A number of them are going to be talking on a panel right after this that I'll talk about. But we have three levels. We have integrated applications. These are the type of applications that you could call directly from nTop. So nTop, these tools, these applications can be run directly from the nTop notebook itself. We have interoperable applications. These are applications that can now natively read implicit data produced by nTop, so you don't need to mesh, no more meshing. And then lastly, we have compatible applications. These are applications where we could exchange BREP data, mesh data, slices, etc. And today, so first I want to focus on 2 new integrated applications that are going live. First off, Intact Solutions. So Intact Solutions is a partner company we've been working with. And Intact produces a meshless solver technology for linear static stress analysis, for thermal, for modal. We're going live with an nTop integrated meshless solve linear static stress analysis. Soon to come, thermal technology. Soon to come, modal analysis. Intact Solution is in the room next door. You can get a demo of this and more. Here we could see a model that's a complex grid-stiffened panel that has a stress analysis run. That field from the stress analysis is now driving the rib thickness of that panel, all done mesh-free. No need to tessellate this implicit surface, so it's very, very fast. Secondly, on the CFD front, Max from Cloud Fluid is in the room as well. I'm really excited to announce a direct integration with Cloud Fluid. And so Cloud Fluid produces a lattice Boltzmann solver running in GPUs on the cloud, NVIDIA H100s. You can set up the model for the fluid analysis. Fluid flow is really important to a number of applications across thermal management, fluid management, like this filter here. And so you could see that model being set up, parameterized by the boundary conditions into it, running through a fluid flow analysis. And so what this enables is really rapid iteration through design changes to the filter, so you can achieve the fluid flow that you'd like in a filter or internal flow systems. Next, I want to talk about interoperability. Interoperability and interoperable applications, these are applications that can natively read implicit files. And so first, I want to talk about Hexagon a little bit. Hexagon produces a solver, SC Stream, really highly useful in the cold plate and heat exchanger application space. And so we've been working with Hexagon to build a direct integration of implicits into their tool. So you can now, when you export a .implicit file from nTop, you could open that up in SC Stream, mesh-free, run the fluid flow analysis, and then bring those results back into nTop for further processing. And so again, the point of these interoperable applications is really to facilitate mesh-free transfer of data for the applications that you guys are trying to solve every day, that you as a set of nTop users are trying to solve every day. Because we've heard you, right? We can produce parts that are incredibly complex, but if you have to mesh that and run the analysis, that is a bottleneck, and so we're targeting that here. Lastly, or second to last, on our interoperable applications, we're going live with an integration into Fusion with Autodesk. Autodesk is also here in the room next door. And with Autodesk, we see here in Fusion, opening up an nTop native implicit model directly integrated into the assembly of a motorcycle. You import that .implicit file, and it opens up, again, no meshing. This is natively reading the nTop implicit, and any of the downstream operations that Autodesk supports on its volumetric object are supported on nTop implicits now. And so this component, the rear swing arm of a motorcycle, if you're at Rapid tomorrow, you'll be able to see this part 3D printed. Actually, we just got the pictures today, and Alex Oster was posting them on LinkedIn, so you can go check that out as well. And so this is going live, and very excited about the potential of nTop Autodesk. And so lastly, I'm really excited to announce a direct integration with Magix 28.0. This is huge. Our customers, Magix being one of the most widely deployed build processors, our customers have been asking for this, and we've listened, we've worked with Magix, and Magix now can natively import direct implicit files. And so I want to take a step back and just look at a customer for a second. So Verilla happens to be the big engine day. So Verilla also produces engines that are massive. So this is but not jet engines. This is an engine like one that would be an ICE in your car, internal combustion engine. But this is the type of engine that powers a shipping container ship. These are massive 18-cylinder engines. And when I was on site at Verilla a few years ago, we were looking at the different components of the engine, and they were saying, hey, we want to redesign a cylinder head. Like, there's a huge business case if we can combine the multiple components of a cylinder head into one component, 3D print it. The new SLM NXG machine just came out, and it could produce, they were talking about printing parts on the meter scale. And so they went ahead and redesigned the cylinder head, reducing the weight, combining the components, producing a really solid business case to make cost-effective components. But the bottleneck was meshing. They couldn't mesh this component. It would take hours in nTop to mesh it. And then once it was meshed, it was taking hours to overnight to open in Magix and weeks to slice a component like this. And so I think one of the most exciting aspects of moving forward with an integration with Magix is the ability now for our customers to directly 3D print from implicit files these components. So as an implicit, this part can be exported from nTop in seconds. I think this part took about 6 seconds to export. Opened in Magix in minutes and sliced in a couple of hours loaded onto an NXG and printed at the proper scale. This is integrated into Magix version 28, which goes live next year. For beta access, this will also be available to customers soon, starting with SLM on the NXG machine. And so we'll hear a little bit more from the next panel on Magix as well, and Materialize is also in the room next door. So very excited for this. And so thank you. But there's one more announcement that I want to talk about. And that's a strategic alliance that we're announcing today with NVIDIA. It was back in 2017 when late at night, me and the dev team were working on implicit sign distance fields. And we had compiled a model that was running on NVIDIA GPUs, updating in real time for a really complex heat exchanger. And this was before nTop. We had a software called Element at the time. And it was clear to me at that point that the implicit sign distance field was the right modeling technology, enabled by GPUs and parallel processing. And so NVIDIA, being the leader in parallel processing and GPUs and cloud GPU cloud GPUs, we're launching and announcing a strategic alliance with NVIDIA to deploy more compute to our customers and to integrate some NVIDIA technology along the computational design process. And so what we've done so far is a proof of concept. We've integrated some NVIDIA rendering technology so you can better view the model as you're building out that computational model. And then second, for running the computational model, we've built a direct and live integration into the NVIDIA Omniverse so that in real time, you can make changes to your computational model in nTop and see those results and interact with those results in the Omniverse environment, integrated into the assembly, with the Omniverse being where all these components come together. And this is also done with native implicits. This is a new entry into the Omniverse, implicits becoming a first-class object in the Omniverse. And so this is just the beginning of the strategic alliance. We're announcing this today and really excited about what's to come. And so, as I said, I think we have a really exciting day of computational design ahead of us. I couldn't be more excited about the conversations to come. We have amazing customers here. We have Stephen from Northrop Grumman. We have Chiara from Okada. We have Ryan from Cobra talking about their deployment of computational models. And so with that, I couldn't be more excited to welcome you to the Computational Design Summit. Thank you.